2D is measures of variation. Okay, so we're looking at how our data is varied or spreads apart. So the first measure of variation you learned all the way back in middle school is the range. So it's just the difference between the maximum value and the minimum value. It just gives us an idea of how far apart our data is. So how far apart is the highest number from the lowest number. Okay, then we have variance and standard deviation, and they both kind of measure the same thing. All right, deviation is the difference between a data entry, so any point in our data. So if we have people's test scores and somebody got a 77, so the difference between 77 and the mean or the average test score. All right, that is called the deviation. And then we can look at two different things with deviation. We can look at variance and we can look at standard deviation. And they both kind of measure the same thing, but we like standard deviation because it gives us units that are similar to whatever units our data are in. So if we have test scores and a standard deviation is 4, it means most of the data values are about 4 points away from the mean. Okay, now these are the formulas for variance and standard deviation. They look complicated, and honestly, to do them by hand, it takes a while because you have to take each number in the data set, subtract it from the mean, and then square it, and then you got to add all those numbers together. It's quite annoying. It takes a long time. So we're not going to do it because we have technology that can do it for us, and so I would rather spend time talking about what a standard deviation mean than calculating it. So in your calculator, you should know how to do one variable statistics, the one var stats. So you type in all the numbers and get that, and it will give you both of these. It will give you the variance and the standard deviation. So we're not going to spend time calculating it. We're going to spend time talking about what it means. Okay, and like we said, it's a measure of the typical amount an entry deviates from the mean. So it tells me, for the most part, about how far away are each of my data points from the average. So again, if I'm looking at test scores, if I have a standard deviation of 5, it tells me that a lot of my test scores are somewhere around 5 points away from the mean. Okay, so just in general, the bigger the standard deviation, the more spread out the data are. Okay, so if I have one class that has a standard deviation of 2 and another that has a standard deviation of 9, then the class with the standard deviation of 9, their test scores are more spread out than the other class. Okay, and so this is what it looks like in a graph. This graph would have a smaller standard deviation than this one because all of the numbers are 4, 5, and 6. They're all close together, whereas here we have some at 3, here at some at 7. The graph is a little bit more spread out. You can also think of standard deviation as a measure of consistency because it tells me how close the data is to the mean or the average. All right, so let's use an example from sports. If you're picking a fantasy football quarterback, do you want the guy that's going to give you 2 or 3 touchdowns pretty much every week? Or do you want to take a chance on the guy that will give you 6 touchdowns one week but maybe 0 the next? Okay, this guy that throws 2 or 3 every week, he's going to have a small standard deviation because if we write out all the number of touchdowns that he scores every week, they're all going to be really close together. All right, this guy, he's going to have a big standard deviation because he might have a 6 or a 5 and then a bunch of zeros, and those numbers are more spread out than a whole lot of 2s and 3s. Okay, so more spread out data, higher standard deviation, and depending on what we're talking about, less consistent performance. All right, the second thing we're going to look at with variation is the shapes of distribution. So if we graph things, if we make histograms, if we make dot plots, even stem and leaf plots, we can see the shape of the distribution. So we're going to talk about what that means. Okay, this would be an example of what we call a symmetric distribution. Both sides, the left and right side of this graph, look pretty much the same. So we have a couple low, if these were test scores, a couple low scores, then we get into B's and C's and they get higher, and we have a bunch of B's and C's, and then as we get into the higher grades, the less people got A's. Okay, so on both ends it's small, and then in the middle it gets big. In this case, if we were to find the mean and median, like we talked about last time, of this data, they would be roughly equal. So a lot of times what you'll see is they will draw a line down here in the graph and say, like, here's the mean, here's the median. Okay, so one would be the mean, the other would be the median. Okay, and in a symmetric distribution, they are roughly equal. They're pretty close to each other. If we have a smaller data set, like if we only had 6 or 7 numbers, a lot of times they might be exactly equal. Okay, so the mean and median are very close to each other in a symmetric distribution. Then we have a skewed distribution, okay, and what they call them is kind of, to me, the opposite of what they look like, but this is actually skewed to the left. And what that means is if I look at the middle of the data, the left tail is longer, so there's more numbers to the left of the middle than there are to the right. Okay, so in this case, the median would be larger than the mean. So my median might be somewhere in here. If I listed out all the numbers, that might be the median, the middle number. Okay, but my mean would be somewhere way down here because all of these low numbers are pulling my mean down. So remember last time we talked about how the median is resistant to outliers, but the mean is not. So these low numbers down here might be outliers, and they're pulling my mean down, but they don't affect the median as much. Okay, so if this is the middle, the median, then there's more numbers to the left than there are to the right, so it's known as skewed left. And this is when the median is greater than the mean. So then we can also go the opposite direction, and we can say that it's skewed right. So if I had my median here, this was my middle number, but then my mean might be somewhere down here. So again, these large numbers down here that might be outliers, or at least they're way larger than most of the data, okay, they're going to pull my mean to the right. They're going to increase my mean, but the median is resistant to those outliers, so it's not going to change. All right, so when the median is less than the mean and there are more numbers to the right of the middle than there are to the left, we say that it is skewed right. And then sometimes in data we have what we call gaps or clusters. So this right here would be an example of a gap. All right, in this histogram, there's a bunch of numbers from 20 to 80, and then there's numbers from 90 to 100, but from 80 to 90 there are no numbers. So like if this were test scores, there's all these people got F's, D's, C's, a couple people got some A's, but there were no B's. Okay, that would be called a gap in the data. All right, and this data has two gaps. It has a gap right here, it has a gap right there, and then these are what we call clusters. So this would be cluster number 1, and this would be cluster number 2. So I have a group in here in the 9 to 18 range, and then I have a group in the 22 to 32 range, but there's no one in this gap here. All right, so sometimes if we have lots of data on either side of the gap, those are what we call clusters. Okay, so that's it for 2D, all right, standard deviation, range, and then shapes of distributions.